All right, hey, this is going to be the video or this is going to be the last video tutorial for my fluids class. We're going to be looking at fluids flowing around a cylinder, both stationary and rotating, with some different Reynolds numbers. So just drag a new Fluent project in. I'm going to go right into Design Modeler. I'm going to start by sketching the circle. I mean, we're really just looking at a 2D cross-section of whatever. So this would be a cylinder if we extruded it into 3D, but in 2D it's just a circle. Make sure the units are in meters. Okay. Now that we have the circle, we need to draw basically a box around it to make the boundaries for the simulation. Just draw out 2 dimensions. We want a 50 by 50 square. So make that 25 by 25. And then draw a rectangle. Then we'll do my favorite. Okay, boundary conditions, midpoint here to here. Oh, kind of laggy, but it worked. And here to here. Okay, now that that's done, we can delete these two. Sometimes it's buggy and it won't let you select stuff. That's just how it is. We'll do surface from sketches. Just apply the sketch, hit generate. Okay, so we have this 2D surface, which is exactly what we want. And oops, now it's time to mesh. So I guess while that's opening, we can just look for this project. We looked at basically inviscid, which is infinite Reynolds number, and then from 0.01 to 20 to 100 to 10,000, then 10 million. And some of those take a while to converge or won't even converge, and you have to do some crazy models. Okay, so for this mesh, we're going to insert method, like always. Select the body. This time we'll do triangles. We'll generate. That's fine. Now since we really want to look at this edge of the circle or the cylinder, we'll insert sizing. We'll just select the edge. We'll do number of divisions, 200. Let's make it hard. 200 hard divisions. You can see it's just really making more cells right at the surface here, which is exactly what we want. You can also insert an inflation, so select the face, and then select the edge. Does it have it? Yeah. Okay, we'll do first layer thickness 0.03. We'll do 65 layers, kind of worked for me. It'll basically just start making concentric nodes getting bigger. So if you do put too many layers, they can actually get bigger than the rest of the mesh, which you don't want. So I'll make the element size 0.2. I use 0.15, but 0.2 is going to take a while to generate, and 0.15 will just take even longer. So it's not going to really matter, but just for the sake of making a not super long video, we'll do that. It's done. So let's just look. See, yep, that's a good mesh. Don't forget to name the sessions, not whatever. Name the edges. There we go. Velocity inlet. We'll call this pressure outlet. We'll control click the top and the bottom. Name it symmetry, and then we also want to name this just wall. So here we have everything. We'll just update the mesh. Now we're done with that. We'll just close both of these and head right into setup. Okay, you want double precision. I'm going to be running 4 parallel processes. I have a dual core processor. I know it's old, but that's 2 threads per core. So I can basically do 4 parallel processes. If you don't do parallel processes, it's going to take a very long time. Let's see. Modern computers have like 6 core processors, so they can run, 3 times. They can be 3 times as fast as my calculations. Just for simplicity's sakes, I'll show you first Reynolds equals 20, just because that might actually converge. The 100, I'll show you how to set it up, but it'll take too long for the video, so I'll just show you my completed simulation and how to navigate a transient model. Okay, so like I said, we'll do steady time. Transient for the vortices is pretty cool to see because you can go time step by time step, but like it sounds, you have to generate, well, you basically have to simulate every time step and do a bunch of iterations. So for steady, you just do basically one, get really good. We will do laminar because, Reynolds number equals 20 is really low. So that would be laminar flow. Less than 2,100 for materials, for fluid, air. And then, yeah, like it's here, we'll do 1 and 1. Very simple. Okay, and for boundary conditions, well, yeah, make sure we have air selected. Yep. We'll hit up boundary conditions for velocity inlet. See, it's the right type, velocity inlet type, and we'll make it 20. So, the equation for Reynolds number is just the density times the viscosity times the diameter. What am I saying? It's rho VD over mu. So it's density, velocity, diameter over viscosity. So the diameter of the circle is 1, so it's just basically 20 over 1. So that's how you get the Reynolds number of 20. Okay, and for the wall, we're actually you can make it stationary first, but I'm gonna make it moving because we have to make it spinning. You can make it 5, sorry, rotational. Don't make it translational. We'll make it rotational, 5 radians per second, but since we actually want it clockwise, we'll do it negative just because the convention is positive counterclockwise. And this way we'll actually get a positive lift coefficient. But it's the same thing if you have it as positive, it would just be, it would be the same magnitude. Okay, so we have rotational, that's all good. Pressure outlet is pressure outlet, yeah. Make the reference values from the velocity inlet. Make sure all that's fine. Okay, so we have to make a monitor here since we want the lift coefficient. Sorry, force coefficient lift. Yeah, lift coefficient. We want a plot also. It'll print out on the side here, like with your iterations. It'll be real nice. We want that along the wall. We don't need to print a console. It's fine. Okay. So that's fine. Now that shows up here. Yep, we have lift coefficient. Cool. Now let's initialize hybrid. We'll just do 25. Okay, so you can see in the console up here. 25 iterations. That's pretty good. It's kind of slow. My computer's been working hard for the past couple days. Okay, initialation's done. just for sake of time, we'll do 500 iterations. If I remember correctly, this one should actually converge pretty quickly. So yeah, here we can see the residuals, but we can also see the lift coefficient kind of generating, and it's pretty stable. Let me show you what happens when you try with some of the other models. Yeah, oops, look, it's already done. Easy as that. But if your lift coefficient starts looking like this after 1400 iterations, you know it's not going to converge. But luckily, we're doing the simple one first. Okay, so you can actually come here. Was compute, and it should show in the console. So it got a lift coefficient of 0.338. If we see here, it's about what it shows on the graph. Yep. And let's just add some of the contours. Same way we did in the previous videos. So there's pressure coefficient. You can just copy it, put it into your report. Do velocity, velocity magnitude. Yep, pretty cool stuff. You can see the mesh if you get close enough, but zoomed out looks fine. Of course, you can change this. Do, I don't know, general. Yeah, looks fine. What else? What else? We want an XY plot, right? Let's just do. We want pressure coefficient, right, over the wall. Yeah, so that's the direction vector. We can also do curve length across the wall. Get crazy stuff going on. That's how you do those two. Let's see. All right, now let's get some streamlines. Oh, and this was rotating, but we can do force report. I usually did with the non-rotating cylinder. I mean, just so you don't change, you know, two variables at once. But yeah, we print here. We kind of, yeah, you can get the pressure coefficients with pressure and viscous. So total is 200. Okay, so sorry, post is already open. So what we're gonna do, oh no, Zoom is thwarting me again. Let's do streamline. We'll do, yeah, what the heck, surface body, start from velocity inlet. Streamline, how many do we want? 500 for velocity. And see how that looks. Okay, looks pretty cool. Could also do vectors. Just do symmetry. That's good. Sampling vertex. If you do vertex, let me show you what it does. It'll kind of make it a lot. It'll make this weird ring. It'll make a lot of vectors just around here because that's where we, have all those inflations for the mesh. So I actually like to do equally spaced and then do like, that's gonna take a bit. Do like 5,000. And hide the streamlines. Well, we can do more than that. Let's do 10,000. Okay, so yeah, you can see the vectors with that. Yeah, so that's cool. You can also do contour. same thing you saw in Fluent. Let's do velocity though. Symmetry. All right, nice. So that looks pretty good. Now that we've got all of that, let me show you how to set up a transient model. Just because, but like I said, I'm not going to run it because it'll take too long. So we'll go to General, set time to transient, and let's see. You can really leave whatever model you want. We'll just leave it laminar. But what you really have to change here. Okay, oops. Okay, so you want to go into calculation and activities. You want to actually autosave every step so that you can actually go into post and look at every time interval of your model. Otherwise, you can't really see anything. And then here it's different. You have to go to calculation. Let's see. Actually, just because. What am I thinking? What am I missing? Reference values is good. Methods, yeah. So we'll do simple. We'll do presto. Second, and then this appears for transient. We'll just do second order. Yeah, that's fine. Okay, then that still auto saves. And then number of time steps. So each time step. Okay, so time step size of 0.01 seconds. That means it'll basically model, every hundredth of a second. And it'll do 250 times of a hundredth of a second. So, you'll get 2.5 seconds basically. So it'll do 50 iterations for each of those 250 time steps. So, it'll take a while to compute all of that. So I'll hit calculate, actually initialize, calculate, just so you can kind of see what it's doing with the intervals. But I'm going to go ahead and stop it and then go into post for the one that's already converged. Just so we don't sit here, because it will take, for this to complete, it would probably take 30 to 45 minutes. It takes a while, at least with my computer. Man, it's even taken forever to initialize now. Oh, no, it's not. Okay, so yeah, you'll see it'll basically run up to 50 iterations, and then it'll do the next time step. Okay, boom, do the first time step, then it starts again. So do that 250 more times. But yeah, we'll stop that right now. Okay, so we'll just X this out. Yeah, that's fine. And then it's good to kind of name your models, because you'll have so many, you will not remember which each one is. So I guess I'll show you the solution for the 100, Reynolds number equals 100. Oops. Just to show you what it looks like, we can see the contours. But yeah, I'm basically just changing the viscosity with each Reynolds number. Okay. All right, nice. So let's see the velocity. So yeah, it gets pretty crazy. You can see all that shredding, which you can't actually see much unless you go into the vector vector profiles, I guess. So let's close this. Oops. Go into post. Hopefully I didn't crash ANSYS. I might have. Okay. All right. Yeah, so this is what I had before. You can see, look, 100,000 vector lines, equally spaced. And now when you get to this many number, this high number of vector lines, if you have it on vertex, it'll look really crazy around here. But okay, so the whole transient thing is you can come up here and change the time step. So let's just come up to 44. And we're basically going back, what was I just on? 49.50. We're going back like 500th of a second and seeing how that changes basically the streamlines. Okay, yeah, so you can still see the vortices forming here. You can actually see a vortex, vortex, vortex. And yeah, you can go to any time interval. Yep, that's what the streamlines look like. The crazy contour. All right, so let's see. I don't think I'm really missing much. I think I about showed everything. Yeah, so just don't get discouraged if your transient models take forever to converge, but they will eventually, and they'll look really cool. All right, and it's just starting to rain. Okay, well, thank you. See you again sometime.